Hello, my name is Antonio Iverdi, and today we're going to be talking about Lab 5, which deals with Faraday's law. The purpose of this lab was to explore Faraday's law through the observation of a magnet falling through a conductive tube of aluminum foil. The falling bar magnet creates a magnetic field, which creates an induced current in the foil. This induced current in the foil creates a magnetic force that will slow the magnet's fall. The interaction between the falling bar magnet and the conductive tube aluminum foil was then modeled computationally. The result of this lab was that an aluminum foil tube slows down the fall of the magnet. Experimentally, the value found for the magnet to enter and exit the tube was 1.39 seconds, while theoretically, we got a value of 1.284 seconds. Some fundamental physics principles used here is the Biot-Savart law for magnetic fields, as shown in the equation on the right. We also use Faraday's law, which states that a change in magnetic field can induce a current. A change in magnetic field of the magnet causes a change in magnetic flux, which then creates an EMF in the foil. We'll also use Lenz's law, which states that induced current flows in the direction so that the magnetic field produced opposes the direction of the change in flux. Finally, we will then use Newton's laws, specifically his second and third law. The second law states that the net force equal to mass times acceleration. In other words, the net force will cause acceleration. And we'll use Newton's third law, which states that every action has an equal and opposite force. The method used in this lab was the use of a magnetometer app to determine the north end of the magnet. We held the tube of foil vertically and positioned the magnet just above the top opening. Then we positioned a smartphone camera to capture the entire tube. The magnet falling through the tube was then recorded, and the time it took for the magnet to enter and leave the tube was marked down. This experiment was then repeated 5 times, and the average time it took for the magnet to fall through the tube was calculated between those 5 trials. As seen from the data and the 5 trials, the average time it took for the magnet to enter and exit the tube was 1.39 seconds. Here's the code used to depict the computational model. As you see in lines 34 to 36, we actually enter in the tube's dimensions. In line 72, we enter the magnetic dipole moment, which we got from Lab 3. Then we calculate the magnetic field using the Biot-Savart law, as shown in lines 97 through 101. We also created a function to calculate the magnetic flux, as shown in lines 114 through 121. As seen in line 148, we then calculated the gravitational force on the magnet. Then we calculated the current in the ring in line 159. Then we calculated the typical Biel field at each ring, as shown in lines 173 through 177. Then we calculated the net force on the magnet, as shown in line 186. And finally, we updated the magnet's velocity and position in lines 191 and 192. Shown on the left side is the computational model itself of the magnet falling through the tube. Now this is just a picture, but this is the end result of the simulation. On the right side, we have the graph of velocity versus time throughout the simulation. And as we can see, the time calculated for the magnet to fall through the tube was 1.284 seconds. Then we are now interpreting the simulation. The red color represents a clockwise current, while the blue color represents a counterclockwise current. When the magnet is flipped, we get the same motion, but the current will be flipped here, due to the change in the flux direction being flipped. Our simulation is different from the real world in the sense that it takes longer in the real world because of air resistance. To make the computational system better, we can account for air resistance, or account for the resistivity in the conductor, or we can even recalculate mu mag, which is our magnetic dipole moment. The velocity versus time graph tells us that the magnetic force and the gravitational force will eventually cancel out. In other words, the net force will be equal to 0. At this time, the magnet will eventually stop accelerating when the forces become equal, and then it will move with constant velocity due to there being no acceleration. If the resistivity of the conductor was reduced to as close to 0 as possible, the magnet would have fallen slower. It would have completely stopped falling if resistivity actually equaled 0. The induced current would be larger, creating a larger magnetic force opposing gravity. If holes or slots were cut into the tube, the magnet would have fallen faster, due to a reduction in rings which would reduce the induced current. The smaller magnetic force would be acting on the falling magnet, allowing it to go faster.